Let's talk about energy.
Energy inside.
Okay.
This is the first time.
Yes, the first time. Energy in simple harmonic oscillators. Oscillators. No, oscillators. So energy in simple harmonic oscillators. We know the differential equation for simple harmonic oscillators. We know that the solution to that differential equation is the position function, some amplitude times, and we'll use the sign. I like using the sign because the derivative isn't a negative. If you use cosine first, then the derivative is negative, which is still valid. It just throws a negative in there in the beginning. So I like choosing sine as my position function. And for reasons that you'll see in a second, I also want to have my velocity function. And we know at this point it should be common knowledge to you all that the velocity is the derivative with respect to time of the position, which in this case is just omega a sine omega t plus phi. So we're going to need those two functions in order, because what we want is a single equation for the energy the total energy in a simple harmonic oscillator that takes into account both the kinetic and the potential energies. All right, and this is for any simple harmonic oscillator, and then we're gonna focus in a little bit on. Actually, we're talking about masses on springs. I'm sorry. So this kind of deal, but the same physics will apply. Yes, gravity is a thing here, and we'll talk about how to deal with gravity in vertical mass spring oscillators. I just don't have the types of springs that are required to do horizontal mass spring oscillators.
Isn't that big cosine?
Oh, it is. I just have sloppy handwriting.
Oh, okay. Yeah.
I like the slow raise there. So we are talking about the energy in a mass spring oscillator. The mechanical energy, I should say. Talking about the mechanical energy. And so the mechanical energy we know is simply the sum, because there's no rotating stuff, there's no spinning stuff. So it's just going to be the spring potential energy. Consider this to be a horizontal mass spring oscillator. So all we have is spring potential energy and kinetic energy, right? So I want an expression that'll make this more simplified, and I'll have an equation for the total energy in the system, the total mechanical energy. So for that, I need to use my knowledge of actually we'll do kinetic first. Kinetic is easier. So let's talk about the kinetic energy. Let's get an expression for the kinetic energy. We know it's 1/2 mv squared, but I can be more specific to simple harmonic oscillators with this as my velocity that I then square, right? So kinetic energy we know is 1/2 mv squared. Well, at any moment in the mass spring system's motion, it's going to have a velocity. Sometimes it's 0 at the amplitudes at 0, but it's going to be velocity. So I can just plug in, and that velocity varies with time according to this function here. So I can just plug that function in for the kinetic energy, 1/2 mass times omega a cosine omega t plus phi, but that v gets squared, right? Right? Right?
Right.
Wow. So kinetic energy is then, I'm going to simplify this, it's 1/2, well I'm just going to square everything. 1/2 mass times omega squared times a squared times the cosine squared of omega t plus phi. And then I'm going to realize that, hey, for a mass spring oscillator, I have a nice expression for omega squared, right? It's in the period equation. We determined that omega is the square root of k over m, but omega squared is just k over m. Right, we showed that early on in this unit. So I can substitute that in for my omega squared that I see here. So the kinetic energy is then 1/2 mass times K over M times A squared cosine squared omega T plus V. And the masses cancel. So here's my expression that I can't simplify anymore. I have the kinetic energy is 1/2 times the spring constant times the amplitude squared times the cosine squared of omega T plus V. So I'm going to put that in my equation holster. And so I want to do a similar thing and get an equation for the potential energy, and then see if there's a way that I can combine those together into a nice, neat little equation. Spoiler alert, there it is. So potential energy. And I want to kind of show something now. Use this as an opportunity to remind you of an equation, a very important equation that's not on the formula sheet that we can actually use to because we know from last year that spring potential energy is 1/2 kx squared. I think when we did work, I think I used that as an example just to show you how you can use, the work equation and the dot product. In this case, dx, right, to determine the equation for spring potential energy. Yes, sir.
You should let Timothy in.
Oh. Do I have to? Sorry, Timothy, I didn't see you there. So we can. I'm recording, right? Yeah. So we can use this to determine the equation for spring potential energy, but let me just use this again as an opportunity to remind you of this equation that's not on the formula sheet, but that is pretty much on every single AP Physics C exam. And that's an expression for force in terms of potential energy and position. If the force is conservative, and ideal springs exert conservative forces. If a force is conservative, then that force can be written as the derivative of the potential energy, in this case it's spring potential energy, with respect to position. Right? Position in general, R, dr. But if we're talking a horizontal mass spring oscillator, then I can just say it's with respect to the position in the x direction. And then I can, and some, like your math teachers in the future will it's a little more complicated than this, but what it boils down to, and for physicers, it's not that big of a deal. I'm just going to multiply both sides of this equation by the differential dx. Actually, I'm going to multiply it by negative dx. Is what I did, right? Yeah. Multiply both sides by negative dx. So I get that the differential, the infinitesimally small change in potential energy, is equal to the force acting, the negative of the force acting times the infinitesimally small displacement that it undergoes in response to that force. Yes, that force changes, right? So we would have to write that force as an equation itself, which we'll do. Right, this force here, I displace a mass on the spring, and I get negative kx, right? That's Hooke's law. The force, the spring force, I should be writing that. The spring force is negative k times x. That's Hooke's law, the algebraic form of Hooke's law. And so I get that the infinitesimally small change in potential energy, spring potential energy, is kx dx. Negatives cancel, kx times dx is what's left. And then we can just do something to both sides to get an expression for potential energy. I can integrate both sides. And again, it's a little more, you can be a little more specific here with the limits and all that, but when you add up all of the infinitesimally small changes in potential energy, you just get the total potential energy. Right? As you're stretching the spring, or as the spring is being de-stretched. So I add up all the tiny energies, and I get the total energy. And that's going to be, well, the integral of kx dx is just from 0 to x. Let's say we displace it from equilibrium. right? A certain distance x. When I integrate this, the k comes out. It's constant. Integrate x dx, we all know that that's just x squared over 2. Hence, the reason that we have the equation on our formula sheet, spring potential energy is 1/2
Boom.
kx squared.
Mind blown.
Good. So that's our potential energy equation, but again, x is constantly changing.
I don't know why you don't see this coming more often.
You will. So now I can plug in this though. I have because x changes. X is a function here. It's a function of time. So I can plug in the position function in for x. And when I do that, I get that potential energy is equal to 1/2 times the spring constant times a sine omega t plus phi squared. And when I square that, I get 1/2 k a squared sine squared omega t plus phi. No omega outside, right? The omega came from when we did the derivative on the position function to get our velocity function. So there's really nothing else we can do to simplify this guy. But what I can say is that if I add these two together, I have the total energy in the mass spring oscillator at any time, right? Time evolves, time passes into the future, so as t increases, then we're going to have these both going back and forth, right? They're going to both vary sinusoidally. As one's going up, the other's going down. And so if I just add those together, I'll get the total mechanical energy. Again, total mechanical energy is just spring potential plus kinetic. So if I add the spring potential, which is 1/2 k amplitude squared sine squared omega t plus phi, and I add to that the kinetic energy, which is 1/2 k a squared times cosine squared omega t plus phi. Well, I told you it's going to simplify down to a nice, neat little equation.
Because sine squared plus cosine squared is 1, right?
You sine squared plus cosine squared. Is that what you said?
Sine squared, cosine squared
Yeah.
is 1?
Yeah, exactly. Now I can't do that right off the bat. I got to factor out the one. Notice both terms have 1/2 k a squared as factors, so I can factor out. Good job, Mr. Nelson. I can factor out 1/2 k a squared, and what I'm left with is sine squared omega t plus phi plus cosine squared omega t plus phi. And as was just pointed out, that's 1.
So mechanical energy equals 1/2 k squared.
Yeah. Mechanical energy is, and this is literally what we expect, but we've just, kind of proven it. All you need to know for a mass spring oscillator is its amplitude and the spring constant, and the total energy that will be in that system. But it kind of makes sense because the normal equation for spring potential energy is 1/2 k x squared. Well, the A is the amplitude. The A is the maximum displacement from equilibrium it's going to get, right? You pull it whatever distance, that's the amplitude. All of the energy right there is stored as potential energy, right? So it's expected, but this is a nice little neat way of showing why, right? Cool beans? It's good times, right? It's good stuff. Good stuff. No questions? May I move on?
Easy.
All right. I don't understand what you're saying.
He has to be culturally appropriate.
You're not being inappropriate back there, are you?
No, I just said that you haven't been culturally appropriated yet.
Oh. I wish I knew Spanish. It'd be good for career opportunities.
I know Spanish when I hear it. I don't understand it.
Oh, that was good. I like that. Okay. So, what I just talked about was for a horizontal mass spring oscillator. That most problems that you'll see, the majority of them will be horizontal mass spring oscillators, but you also have vertical mass spring oscillators. The difference is I have spring potential energy, or I have spring forces. I have velocities, kinetic energy, but then I also have gravity. Gravity's doing stuff here. They couldn't see it on. So gravity's at play here too. So that's what makes vertical mass spring oscillators a little more tricky to deal with. However, as we'll show now, it's not really that much trickier. It's not that much more trickier.
I thought that was backwards. You went backwards.
What?
You said, never mind.
Okay. Don't confuse me, Bradley. Okay. So let's say I have a spring. Actually, let's do this in real time here. So I got a spring that's hanging like that. So no mass attached to it. So that'll be that spring there. And then I hang a mass on it and let it find the equilibrium point, and then just let it chill there at equilibrium. So that'll be this one. So now it's at equilibrium. And I'm going to define down, just for convenience sake, as my positive y direction. And so I have a displacement here. The spring has been stretched. I'm going to call that stretch, and I'll measure to the center. I'll call that YEQ. EQ for equilibrium. Right? It's been stretched downward a distance y, and now it's in equilibrium. So I'm going to call that the equilibrium position. Right?
Just go to the top of the block.
What's that?
Wouldn't the YEQ just go to the top of the block since the spring is connected to the top?
Okay, if you're gonna be a stickler.
That's what I was thinking. I just didn't say it.
Well, how do you know? Maybe the spring goes through a hole and is attached right to the center. How do you know that's not the case?
That'd be really difficult to do.
You can do it. There's holes down here. Anyway, obviously we're gonna measure to the top of the object. And it's going to stretch a distance, YEQ. We'll call it YEQ. And then, obviously, if I stretch it more, it's going to oscillate with amplitude A. Well, I'll call it the amplitude A. That amplitude is the distance from equilibrium to wherever I stretch it to, and then let go. So I'm going to pull it down even farther.
Oh no, this spring's gonna break.
Pull it down even farther. And so the amplitude then would be this distance. So I call that distance A. Now in the second situation at equilibrium, what can I say about, there's two forces acting. What can I say about the spring force and the weight force mg? What can I say about them?
They're equal and equilibrium.
Yeah, this is equilibrium. So at equilibrium, they have to be equal because it's not accelerating. The block is not accelerating. So the spring force and mg are not accelerating. So let's just do a quick application of Newton's laws to say that the spring force is equal to the weight force mg. Right, I could say, well, I know the net force is 0. It's been a while since we did something like this, so let's just do it. I know the net force is 0. The net force I define down as the positive direction. So I have mg minus the spring force, which we also know is... Now I don't have to put a negative here now, right? That spring force is pointing up, so it is negative. Negative k times YEQ. It is in the negative direction because I define down as the positive direction. So it's mg minus spring constant times the equilibrium position equals 0. You all with me?
So, would it be plus in that case or not?
No, when you draw a free body diagram, use the direction of the vector and your coordinate system to tell whether the force is positive or negative. It is the negative here. I noticed that it did stretch downward in the positive direction, so the force is a restoring force in the negative direction. Now here, what direction is the net force going to point? Whenever I stretch it farther down. It's going to point up, which means my new spring force must point up. And so the total stretch here, that force is going to be negative k times the equilibrium position plus the amplitude, right? So when I apply Newton's second law now, because we will have acceleration, obviously when I stretch it, the instant I let go, it has acceleration upward. That's why it picks up speed upward. The net force is going to be mass times acceleration, Newton's second law. The net force is a positive mg minus spring constant times the equilibrium position plus the amplitude. Right? And that equals ma. Well, something interesting happens whenever I distribute the spring constant over both the vertical displacement terms. I get mg minus k times equilibrium position minus k times amplitude equals ma. How can I simplify my life here?
0. So it would just be negative ka equals.
Yep. mg minus ky eq is constant. Right? There's nothing varying in that part of the expression. So mg minus ky eq is literally 0. Nothing changed there. The equilibrium distance is the same, spring constant is the same, mg is the same. So I get negative k times the amplitude is mass times acceleration. Well, this is just the net force. Mass times acceleration is just the net force. So the net force on a mass spring oscillator when you stretch it is just equal to negative k times the amplitude. What that means is when you have a problem dealing with the mass on a spring, you don't even need to worry about the vertical stretch initially unless you need that information to get the spring constant. Some problems have you do that. They say when you hang the mass and let it rest at equilibrium, it stretches a certain distance. Well, you can figure out what k is in that case using this, right? Using the equilibrium condition. But then after that, all you care about is the amplitude. So you don't need to worry about the gravitational stuff going on, which is convenient because it gets trying to track 3 different energies changing at the same time would be complicated. But what we can do here is just say, well, just ignore gravity as long as you're using the amplitude, the distance not from the unstretched position of the spring, but from the equilibrium position of the spring. Cool.
Gravity's not even real anyway.
It's not real anyway. So always ignore gravity.
There's no
If the AP exams ask you a question about gravity, just say it's not real.
Just say it's not real, and I reject the premise of this
They
question.
can't count it wrong.
They can probably still count wrong, but
They can only not give you points for it.
I wonder if there were like flat earthers on the AP exam, like doing weird stuff.
there probably is, or just students that don't know what to do, and so they just make up some weird stuff. Your dad has done grading before, I imagine.
Yeah, he's done some writing too.
He's probably seen some interesting stuff.
Yeah.
I would probably do that if I was taking an AP exam and I had no idea what to do. I would probably try at least something and then just write some funny stuff to make the grader laugh.
Yeah.
And then they probably just get annoyed with you. Okay. Why do I keep putting this back? What if instead of having, note the period here. Pretty small period, right? Note, or what if I hung another spring on that? Larger period, right? you can't really tell. Well, maybe you can. The spacing of the coils on this guy is a lot smaller than this one. So they have, you can see, right, if you're in the front. So they have very different spring constants. So that means that this guy's going to stretch less than this guy is. This guy stretched more than this guy did. So I would say that I could call this guy X1, right? This is spring 1, spring 2. This guy has spring constant K1, spring constant K2. Whenever I stretch them both, this guy's going to have a displacement X1. This guy's going to have a displacement X2. The total displacement would be X1 plus X2. Are we cool with that? You can wrap your brains around that? Okay. So we call these springs in series. And did we even get to circuits in AP Physics 1 last year?
No.
No, because that wasn't going to be covered. You don't remember that? Because that wasn't covered on the AP exam, right? So we stopped before we got there. Okay.
Yeah, exactly.
Exactly. So what we'll see is that when we learn about circuits, because we'll spend a lot of time on circuits in this class next unit or next semester, what we'll see is that resistors and capacitors in circuits actually function very much like springs in series and springs in parallel. Resistors, capacitors in series and parallel, they behave very much like springs in series or parallel. It's kind of weird. It's just the way the math works out. Now, very similar ways, but then they're kind of flipped. Like springs in series operate like resistors in parallel, and springs in parallel operate like resistors in series. So it's flipped, but if you understand how one works, you understand how the other one works. You falling asleep back there?
No.
Where are you pointing at?
I was pointing at Joel.
Oh. Stop pointing at Joel. Okay. So let's say I got two springs. And this is, let's say that's where the equilibrium position was. But then I stretch them, so there's spring 1, there's spring 2. And I attach them to a block, and then I stretch it from the equilibrium position. When I stretch it from the equilibrium position, I get a displacement. I'm going to measure it to the center of the block, Trenton. And that stretch is going to be X1 plus X2. It's hard to draw X1 and X2 here because it's just difficult. So I'm just going to add them together. That's the stretch, the total stretch, both springs together. And in response to that stretch, I obviously get a spring force in the opposite direction. Now, and I'll bring this up again when we get to resistors and circuit elements that are wired in series or parallel because it's difficult stuff, it's tricky stuff. But think of it as when we get there, it'll be from the battery's point of view. Think of yourself as the battery. Consider yourself to be the battery. What are you, and you don't have eyeballs, just what are you feeling as you're driving the circuit? Well, this mass here doesn't have eyeballs, and so all it feels like is it's being pulled by a single spring, right? It's like, well, I have one spring that's pulling on me, making me move. But there's two springs. But he only feels one. He only feels one spring. Right? And that one spring it behaves like the combination of the two springs here. And so from the block's perspective, from the mass's perspective, he feels a spring force that is equal to, according to Hooke's law, the negative spring constant that would be, if it was a single spring, that would have a spring constant equivalent to how the two spring constants together behave. So it feels, we just saw that. The effect on this mass, which doesn't change, whenever I have two springs in series, these are in series, in parallel, they're literally parallel to each other. So these springs in series, they function very differently than if I was to just have a single spring. Right? That mass there is like, oh, there's this very different motion than it was before. Right? Even though that mass only feels itself being affected by a single spring. So what we do, we call that the equivalent spring constant. It's the spring constant for a spring that literally isn't real, but if it was real, it would behave exactly like the combination of the two springs. Does that make sense? So it's usually, the vast majority of the books, textbooks, and teachers will call it the equivalent spring constant. When we talk in circuits, it'll be equivalent resistance. equivalent capacitance, equivalent inductance. So we have negative spring constant times the total displacement, which is x1 plus x2. Right? Okay. Now notice that the just like a rope, when you put tension on a rope, you have the same tension throughout the entire rope, right? You have the same tension throughout the entire rope. You pick any point in that rope and you have the same tension force pulling in both directions by Newton's third law. So I have this spring force that's acting on the mass is the same spring force that's acting on the wall where it's connected, and it's the same spring force that acts throughout the entire thing. But if I just zoom in on one of the springs, say spring 1, sorry, I should have labeled them as such. Let's call spring constant 1, spring constant 2, spring 1, spring 2. I can say, well, this same spring force is equal to negative K1 times his individual displacement. Right? Hooke's law says that that's going to be, the force is the same throughout, but if you look at spring 1, it's displaced a certain distance, x1. So if I'm just looking at spring 1, it's displaced a certain distance, and according to its actual spring constant, it'll have a force, a spring force, throughout its entire length, acting on whatever it's connected to. But that force will actually be the same force as this guy. It'll be the same force because it has to be. Because once you stretch it, if you just hold it there, nothing accelerates. So the forces all have to be the same. Similarly, I can say, well, that same force is equal to negative K2 times x2. So if I look at from the perspective of K2, or spring 2, it's displaced a different distance than spring 1. So that different distance times its spring constant gives you the same value as well. That's why the stiffer the spring has the higher spring constant, smaller stretch, right? Whenever I stretch these guys again, I stretch these. This spring has stretched pretty significantly farther than this spring. The coils are much farther apart. I'd say about, maybe not half, or twice as much. But the coils are they're spaced much farther apart. The force has to be the same throughout the whole thing because nothing's accelerating. The force has to be the same, because nothing's accelerating and because of Newton's third law. So the force is all the same throughout. So the force that this guy's exerting on my finger is the same that this force is exerting on the connection point up here. And so the same force, well, how can they have the same force if they're different spring constants? Well, just the one that has the higher spring constant has the smaller stretch length. Right? It makes sense, right? Come do this if you want. If you need to feel it in your gut.
Oh.
What?
Man, that's a weird place to feel a spring.
Yeah. Yeah, that would be, yeah. Okay. Now the reason I'm doing all this is because we want an expression that will allow us to calculate the equivalent spring constant. And again, we're going to see this when we do resistors. When we do electric circuits, basic electric circuits, we're going to do a very similar thing to talk about the equivalent resistance. So it's very important. You don't see springs in series that often in everyday life, but there's resistors literally everywhere. Right? Anytime you have electricity, you have resistors. Resistors are used for a lot of different reasons, but mainly to just control the amount of electric current flowing through a circuit. In your phones, yes, there's little tiny resistors in your phones. So I need an expression for the equivalent spring constant, right? I want an expression that will work for all mass spring oscillators where you have springs wired, connected in series. That's what I'm looking for. That's the whole point of going through this. So what I can do is just say, well, if that spring force is equal to this spring force is equal to that spring force, I can just set them equal to each other. So just for the heck of it, I'm going to set this spring force equal to that spring force. So I'm just going to say this is equal to negative K2 times x2. Right, I know this spring force has to equal that one. I'm trying to solve for KEQ in terms of things that are constant. Okay. So in terms of things that I just have a nice, neat expression for that will apply to all mass springs mass spring oscillators where the springs are in series. And then I can use that KEQ in the simple harmonic motion equations, in the period equation, and all that stuff. So what that means is that I need to get rid of x1 and x2, because x1 and x2 are specific to this particular situation. I want them out of the equation. I want KEQ in terms of k1 and k2. Can you see, understand like why that would be a thing? Okay. So first thing I see here is that, well, I can't do that. I have x1, x2, and x2 here. I can't do that. But what I can do is equate these two equations. And when I do that, check out what I can do. Negative k x1 equals negative k2 x2. This is k1 x1. Because really I have three equations, so I should be able to eliminate two of the variables with some algebra. I can multiply both sides by -1, so I can get rid of the negatives. And then if I solve that equation in terms of x1 by dividing by k1, I get x1 equals k2 x2 over k1. And substitute that into here, then everyone will have brought x2 to the party. All right. This guy then becomes negative k, and actually I can multiply both sides by -1 here to get rid of the negative symbol. And I substitute that for x1. So I get KEQ times k2 x2 over k1 plus x2 equals k2 x2. If I distributed KEQ over both of these terms, then I would have three terms, and everyone will have brought x2 to the party, right? So I can just divide both sides of this equation by x2, and the x2's go away. And I eliminated x1 by making that substitution. So now I have an equation that is just in terms of k, all the three k's. So I have KEQ times k2 over k1 plus 1 equals k2. Number of ways you can go about doing this. The way I like doing it, I don't like dividing and multiplying by numbers written like this, mixed numbers, essentially. So I'm going to go ahead and write that as a single fraction, which is going to be k2 plus k1 over k1 equals k2, right?
Shouldn't it be just multiply stuff?
You put KEQ equals.
What?
Say KEQ equals
I don't know what you're talking about.
on the left side.
On the left
is
side.
Equal sign. Yeah.
I don't know what you're talking about. Oh, how embarrassing. There, you happy now? You happy? I did it right, okay?
About
Oh, Tom, God.
Sorry. Okay. Well, then I can divide both sides, which means multiply by the reciprocal, right? So I get KEQ equals K1 K2 over K1 plus K2. Now some students will use that form of the equation, but the majority of the time that's not how it's given to you. And in fact, yeah, the way that, because you don't get the equation for this, but you do get the equation for how to deal with resistors in series and parallel on the formula sheet. This is now not how it's written. It's written as a reciprocal relationship, because then we can actually simplify this a little more. If I just divide 1 by both sides, I get 1 over KEQ equals K1 plus K2 over K1, K2. And you'll see why they do this. Because now, right, I can break this into two terms. And when I do that, I get 1 over the equivalent spring constant equals 1 over K1 plus 1 over K2. Right? Because this right here will end up being K1 over K1, K2 plus K2 over K1, K2. So I got 1 over K1 plus 1 over K2.
that makes
If there's more than two springs, that's it. there's 4, there's 5. You just continue it on. How it's written in now. This is springs in series. Resistors work like this, but they are in parallel. The way they work, they follow the reciprocal relationship when they're in parallel. So you'll get the equations for how resistors work in series and parallel. So just think in the opposite for springs. So resistors in parallel, you'd say 1 over the equivalent resistance is equal to, this is how it's written on the formula sheet, the sum of all the 1 over R i's. Okay, that's how it's written on the formula sheet. And I think it says 1 over RP actually. Yeah, to tell you that it's resistors in parallel. They put a P there. So understand that the springs work the same way, only its springs in series function like resistors in parallel. It's opposite. And so this, usually you don't have more than 2 springs in series or parallel. So generally it's just that there. That there.
Are we ever going to calculate anything with like shocks on a car?
Calculate what?
Shocks for a car? Because
I almost put a problem like that on the quest assignment. But it was too basic.
oh,
Like actual shocks? Modern shocks are more than just springs though. I mean they're very technical. Way beyond my knowledge. But yeah, shocks are springs with very high spring constants, right? Because they must be very stiff. But also not too stiff that they don't absorb impacts. But
not too stiff to where they just shatter and break.
yeah. Or tear your car apart because it vibrates so much because it's not having the shock. I can't talk anymore. Is it Friday yet? Gosh.
It is certainly Tuesday.
Oh.
It's Friday, but it's spelled Tuesday. And pronounced Tuesday. It's Friday.
And there's still 3 more school days before Saturday.
Before, yeah.
It's Friday minus 3 days.
Yeah.
Okay.
Today is still 72 hours.
It is F minus 3.
Today equals Friday minus 3.
I love nerd humor.
Friday is at least a half day, I guess.
You have some nerd humor? Nerd humor?
Sure. Humor.
Have you seen this?
Oh no,
No, I have not.
I'm scared.
No. I almost messed it up.
Irrational. Yeah.
Oh, that was bad. Okay, let's do something that's far, far more complicated than springs and series.
You only have 1 minute left.
And that will be... What?
Go home.
Shut up, Trenton.
I'm using.
Let's do springs in parallel. Far, far more complicated.
Uh-oh.
So here's the equilibrium position. I displace it to the middle. I'm measuring to the middle a distance x. But even if the spring constants are different here, which we can assume they are, let's say m is so heavy that it's not going to be the stiffer spring isn't going to cause it to rotate. Okay, let's say that the weight of m, the mass, is just keeping it so they both get displaced the same distance. So the force on this guy, again, the mass itself, it doesn't see the springs, it just feels the effects of them. And so we could say that mass feels like it's being pulled by a single spring, whose equivalent spring constant, were it to exist, would function just like the combination of these 2 springs. Right? For any 2 springs acting on an object, you can think, well, there's a spring in the world somewhere that's going to act in the same way as a single spring. And so that's what we're looking for here. Well, I know that spring force is simply negative. Well, I got 2 spring forces, right? I got one from K1 and one from K2. So I got negative K1 plus negative K2, or minus K1 times X minus K2 times X. Right? That's the net force, the net spring force. There's two of them, but the distances are the same. X is the same in both. And again, we're saying we want to find out what the equivalent spring constant is. So we just set that equal to the negative, to this force essentially right here.
Everyone brought X to the.
Everyone brought X to the party. Everyone brought -1 to the party.
So it's just
So KEQ
it's just K1 plus K2.
is K1 plus K2.
Huh.
And so,
That's too much.
yeah, it's too much. That's why I ended it with that one, to scare you guys. And so just like, so this is springs in parallel. Resistors in series work like springs in parallel. So the equation for resistance, the equivalent resistance in series, is just the sum of all the resistors. And so if you have 3 springs, it's K1 plus K2 plus K3. Okay.
I think this right here is what's driving me away from majoring in physics.
This right here.
Yeah, this is
That's a single equation.
Yeah, that problem right there.
What about 2 plus 2, Connor?
what is that?
All right, that's it for today.